What's the pressure rating on this pipe, you ask? The pressure rating is China. In this video, I'm going to build a robust hydrogen synthesizer. Now, I've built these things in the past out of plastic bottles and glass jars and stuff, and they're just not adequate for large production. They get too hot, they start boiling over, and all kinds of nasty things happen. You can end up with a really dangerous mess on your hands real quick. So essentially what we're going to do here is I'm going to assemble a canister that's capable of withstanding a aluminum and sodium hydroxide reaction. You should never try this. It's an extremely dangerous process for several reasons. Before I get the reaction going, I am going to explain a couple of details about safety issues concerning this. If you don't want to listen to them, go ahead and just skip through it, but you need to understand something. If you have plans of building something like this, you need to remember there are two significant factors that inhibit you from building a high pressure device. Actually, there's three. The first one being something called stress corrosion cracking. You need to look it up. Anytime you have a caustic solution under pressure inside a steel canister, the hydroxide ion does something to the metal. It migrates inside of the steel lattice and causes a weak point, which can induce a crack, especially if there are stresses inside the structure. Secondly, you have a phenomenon called hydrogen embrittlement. You need to look that up, which has a very similar effect, is where hydrogen gas seeps into the metal lattice of the molecular structure and causes weaknesses and disturbances in the magnetic and electrostatic attractions of the molecule, or something to that. That last comment was very speculative. I'm not a quantum physicist, but it's something like that. Third, there's another problem with high pressure systems like this that you need to understand. When you're working with high pressure, there is a third phenomenon known as adiabatic heating. And what happens is, when you suddenly fill an enclosed container with high pressure, say we're going to use a regulator for example. Let's pretend this is a pressure regulator. Let's say we cracked a little valve that suddenly filled this small void with 2,000 psi's. What that does is causes a heating of that area, because the amount of thermal energy inside that air is more than can be dissipated by the surrounding area. It has to equilibrize. So what happens is, when the air molecules rush in, there's so many of them and they come in so fast, they impact the walls of the chamber and heat it up. And if the surface area isn't large enough to dissipate the heat quickly enough, little tiny burrs or microscopic imperfections in the machining will ignite and can ignite the gas. And not only can it ignite the gas, if the components are aluminum, it can cause a thermite type explosion and pressure surge in the tank. Man, I'm going to be babbling on for a while here. I apologize, but this is important. There is also another phenomenon. So we're going to go ahead and say there's a fourth issue that can kill you when you're messing with this stuff, and that is electrostatic discharge. Now, anytime you have a gas, any kind, a liquid or just a gaseous gas flowing through a line, you are causing a static buildup if that system is separated by a dielectric. For instance, a rubber hose, a EPDN tubing, or a nylon tube, or a PVC tubing. Anytime that gas is flowing out of this chamber through this valve, it is taking with it electron charge and causing a potential difference that builds up over time until a little spark will ignite. There are videos of this phenomenon taking place with hydrogen generators. Daniel C. 2008 has a video of this phenomenon taking place. So that little spark could ignite the gas inside of this. And I know you're thinking to yourself, oh, it's pure hydrogen, it won't ignite. Well, you have to remember that the chamber has a column of air inside of it when you close the cap. So there is oxygen that you need to purge out of this. If you don't purge this tank of the residual air, you could be headed for a disaster. So if you have toughed it through this, you're a champ, because that was an awful lot of battling. But like I said, there may be some dangers that I haven't even mentioned yet here. If you know of any, leave them in the comments of what else you think I might be thinking of. The whole idea is one of those situations where you really need material compatibilities that are beyond the pay scale of this video. If I was on Patreon making 12 grand a month or something, this would be a nickel tube, and we'd be pressuring this bad boy up to 1,000 psi's. But that ain't gonna happen with some $70 worth of black steel. So we're gonna get on with the experiment. I'm gonna build this thing. We are gonna be pressuring it up to about 200 psi's, because that's a safe pressure, irregardless of the issues I've discussed. And the reasoning behind that is it will keep the boiling down. Not only will it increase the boiling point of the solution used to liberate the hydrogen gas, but it will decrease the size of the bubbles significantly, reducing the foaming issue, because foam will attempt to rise up this column, kind of like toothpaste squirting out of a tube, and cause some serious issues. So that's the one thing we've got that may be causing us a problem here. This foam may want to try to rise out of this. Now, to make this reaction interesting, I am going to initiate the very same reaction in a visible container, so that we can observe the reaction rate while it's taking place inside a opaque container. Now, I do understand that because this will be under pressure, the reaction will in no way be the same, but at least we'll know where we are as far as how much aluminum's left, how powerful is the solution still, because it dies off over time, and that's where we are. I'm going to shut the hell up and get on with it. Alright fellas, so I'm in the middle of building this death trap here, and I'm getting ready to tap the threads for this brass needle valve. And these are basically 18 threads per inch. And I just thought I'd show you guys a little bit of the building process. Maybe you can see why some of the stuff I build is a little crooked. I'm always in such a huge hurry to get stuff done. I'm really kind of worried about this thing. So basically what I'm going to do is I'm going to thread this, drill it in place. After it's been threaded in place, I'm going to solder this thing on here as well, because I don't trust just the threads alone. I don't want them to leak. I don't want to use Teflon. This thing's going to be pressured up with hydrogen, and it's going to have some hot caustic soda inside of it. I have been reading up on hydrogen embrittlement and stress corrosion cracking. A couple of things I discovered is that a lot of it's temperature dependent when it comes to the stress corrosion cracking. If we can keep this thing under 140 degrees, the iron won't be susceptible to cracks from the caustic solution. Now, as far as the hydrogen embrittlement, it turns out hydrogen embrittlement is only an issue. This is a quote from a scientific journal and some lab testing. It was only an issue in its nascent form. We've all heard or seen the formula for water, H2O. Well, hydrogen is usually in diatomic form. So is oxygen in the atmosphere, O2 and H2, you know. Well, when you have just a single hydrogen atom, it has a tendency to sneak into the metal lattice of the structure of the crystal. And if there are stresses in the metal, it's even worse. Imagine the metal being stretched apart on an atomic level and being made just a little bit bigger, and those hydrogen atoms get inside those stress regions and cause failures. But anyway, the hydrogen embrittlement through nascent oxygen was discovered way back in the 1930s. A scientist had put some metal samples into a vat of acid and discovered that after almost immediately being submersed, they lost a tremendous amount of their tensile strength. Just for seconds. A piece of metal being immersed in acid for mere seconds can lose a huge amount of its tensile strength. I'll try and find the actual specs, what they were claiming, but come to find out what was happening was it wasn't the acid that was weakening the steel. It was the nascent oxygen being developed or liberated in some type of reaction between the acid and the steel. So essentially, what happens is that nascent oxygen gets into the metal, but here's the thing, it can be reversed. I believe they said just after letting it stand for a while, the hydrogen could creep out, and also heating it up would completely reverse the process. So the dangers of nascent oxygen are there. I'm going to probably paint the inside of this entire thing. What I'll do is after I solder this, I'm going to put a little cork in there. I'm going to paint these pieces, and hopefully using this here paint will stop any of the sodium hydroxide solution from contacting the steel and the nascent oxygen, if any is even liberated in this reaction. It may just be straight hydrogen. I'd really have to look into that. Either way, this whole thing's going to be incredibly dangerous, and I should not do it. But you know what they say. So that's that. I'm going to solder this bad boy on here. Alright, even though I'm using acid core flux, I like to drop a little actual solder flux on there to boil some of the scale and oxidation away while I'm heating everything up. Now the back side of this is covered with oil, but rather than waste time cleaning it, I'm just going to burn it off during the process of soldering the front side of this. I'm not necessarily calling that cutting corners, I'm just trying to save time here and effectively solder this thing at the same time. This is acid core solder, 4060. Some good stuff. All right, that's a pretty good fat bead. Let's hope that saves my life here. I hope no one decides to be stupid enough to build this thing, because I'm telling you, you can't go at high pressures with this stuff. There's a lot to it. A lot of people might not watch this whole video and hear my safety warnings. This is a stupid idea. I'm doing this because I want to build a hydrogen synthesizer that can liberate a huge amount of hydrogen in a very short amount of time. I've got a couple of ideas that I want to use this for. I want to try and build some kind of like a fuel cell, temporary battery setup. And I was also interested in building a couple of little weather balloon type things. A couple of experiments that require a weather balloon, that is. So, there we are with that solder joint. Now, I'm going to wash that off. I'm going to wash that flux off using a little trick I learned back in Nam. Okay, now, so to get this flux off, I'm going to heat it back up till it starts to simmer, the flux that is, and then blast it with some water. And that damn near cleans it up almost good as new. I could probably do that one more time, but I ain't trying to get all pretty here today. As I was grinding the word China off of this end cap, I thought of something. I wanted your guys' opinion. I kind of messed up here on the build. I regret buying this piece now. I initially bought this plug because I believed it would be easy to remove it during the process of use by just being able to simply put a wrench on this. But now I'm starting to think I may have reduced the pressure rating of this thing even further, and I might even be creating a lot of that stress they were talking about in those scientific journals regarding the nascent hydrogen. When this thing tightens down, it puts a huge amount of stress on this outer band to our disadvantage. It kind of wedges it apart. So the tighter I get this, the more internal stress is going to be already acting on this ring. Now with an end cap, like on the other end, I don't have that problem. In fact, it's the opposite. With an end cap, not only do I have this secondary solid band, but it's actually pre-stressed to our advantage. So I'm a little disappointed. I made a big mistake there in my opinion. This thing is rated with a burst rate of 7,000 psi's. What's the pressure rating on this pipe, you ask? The pressure rating is China. I don't know if I like it. Man, I wish I had one that didn't say China on there. Okay, so we're going to reduce the initial operating pressure by 100 psi's. I think I'm just going to keep this thing around 100 psi's. That will keep the boiling down a little bit so it isn't frothing over. I hope. That's the idea behind running a pressurized reactor. I'm not going to pressure this thing up to thousands of psi's, but I am going to run it at pressure so that the foam is reduced significantly. And also the bubbles from the boiling will be smaller and we'll be able to generate more hydrogen in a smaller container. That's the idea behind the pressurized operating cycle anyway. If you've never used a step drill before, you really ought to check one of these things out. They're pretty awesome. I've only recently started using them. They're perfect for drilling wide holes through thin material. This is a Harbor Freight version. If you don't buy them at Harbor Freight, you're going to pay about 50 bucks for them because they're pretty expensive piece of metal. These only last several holes though if you buy them from Harbor Freight. But they do self-tap iron. I've got to get this thing done. I'm not 100% positive, but I think these are a class 1A or a class 1B thread. So if you bend them up a little bit, it's not the end of the world. You'll still be able to assemble it pretty easily. I could be wrong on that. I'm no expert when it comes to threads. Okay. A little bit more on that. This vise has had it, man. I can't believe this thing's still going. This has been burned, doused, smashed, everything you can think of. Yeah, I might bore that out just a little bit more. It's not quite where I need it sticking out in the end there. Just a little bit more. Yeah, I should have spun that on first. Okay, I think that'll do it. Yeah, if I get that hot enough, get that good enough cleaned up, I should be okay. Okay, I think I can get a little bit of a bead down in there. What I'm doing now is kind of abrading it, which is I'm kind of trying to rub the scale off of there and introduce excessive amounts of acid into there to help burn off any scale or oil. I don't really want the solder, but I want the acid core flux to get onto the part. So that's why I'm adding this huge amount. This is going to be a pressurized part, so I'm not trying to skimp on solder here at all. So here we are, we're gonna solder some steel here. I don't want to use Teflon tape for this, and if I ever need to take this back apart, it comes right back apart, so it's not all that big a deal. I prefer this over Teflon tape, or something like this. I don't know about this one. Okay. Seems to be falling down into the threads, so hopefully I'm getting lucky here. Yeah, it's going in there. Have to cool that down before it damages my lower joint there. Okay. I am out of solder, but I'm hoping that got it. I have some lead-free acid core solder that I'm gonna try, but I've never had luck with lead-free acid core solder in my life, so we'll see how that goes. We'll soon find out whether or not that'll hold. I'm going to pressure this up with air and leave it pressurized. See how long it holds air once we're done with it. Now for that part. Put a bunch of flux on this thing. This may not work out too good. I may end up taking this right back apart. I don't know how this is going to go. I have this here Lennox lead-free. It says acid core, so we'll find out. Seems to be flowing okay. Keeping that heat down towards the bottom because that's where I want the solder to flow. I like to get a little tracer going first and then come back around with some heavy solder. That way I don't carburize off all the flux that I applied. Okay, water bottle. It's like a cold spot right there. I'm gonna have to hit that again. water really seems to clean off that scale. The solder's flowing real nice now. Definitely liking the water trick. See how that solder just flows on that metal now? Before we wasn't getting that really. Okay, I think I'm going to hit that end cap again with this stuff. This stuff's doing a lot better, giving me a good joint. Big old mess. Yeah, that joint looks a lot better than the other one. And that was with the anti-money. I've never had luck with that stuff in the past. Then again, I probably wasn't using it on steel. So let's look into this here. Yeah, I think I might give this thing a hit. I don't like what I'm looking at right there. It looks horrible. So I'm going to heat it up and then give it a water blast and see if that helps this bottom joint out any. It's the first time I've ever tried soldering after doing the water blast, so I might have stumbled on a nice little trick here. It definitely leaks. I just seen some water spray out of it. Okay, cleaned it up, a little water there. Let's try that trick now. See if it works out at all. Hard to say. It's kind of a really blackened edge right there. Now I didn't just clean this up with a grinder or whatever because in the past I haven't needed to. I've managed to just be able to abrade it, which is when you kind of scratch it. Yeah, I don't know about that joint. That looks a lot better now. It's got that nice wet look going. I think I'll take it. Run one little zap on it. Now, a lot of people are going to probably call me an idiot for spraying water on a fresh solder joint, but I've been doing it for quite a while and haven't had any problems yet. Not even on some of the structural stuff I've built with solder. Doesn't look the prettiest in the world, but I wanted to get all that flux off of there. Okay. And I'm done with it. So I've done a leak test on this thing by filling it with air, and it does leak. So I then had to do a water bath test by dipping it in water. I didn't feel like getting soap solution all over the place, so I just filled the sink up with water, and air's leaking right there, as you can see. I probably could have just did a quick spray and figured that out on this one, but I didn't have anything on hand at the moment. So what I'm going to do is completely take this off, and I'm going to try and do a really good job of making a conical application of the thread sealer. I'm going to try to taper it off, basically, is what I'm saying, rather than make it so fat it doesn't wedge in there. So that's where I'm at. Currently leaking like crazy. And once I get the leak situation figured out, this pretty much means it's about ready to paint. I have to paint the inside of this thing because further research has indicated that indeed nascent hydrogen is liberated in the process that will be taking place inside of the synthesizer. So we're going to have to paint it. I don't want this thing blowing up on me. As I said, I'm only going to hit 100 psi's, but still,